In this video, we're going to be looking at the second part of topic 16a, which is electrochemical cells. So this is taking what we've learned about standard electrode potentials and applying it to these cells and feasibility. And this is part of the Edexcel International A-Level Chemistry course for year 13. So we're going to be looking at how we write out cell diagrams and the importance of the conditions when we're measuring these electrode potentials. And we've talked about some of that previously in the standard electrode potential video. We're also going to then use that information to predict the thermodynamic feasibility and look at the link between the E cell value and the total entropy and the equilibrium constant for a reaction. We also need to consider some of the limitations in terms of kinetic stability, which again we've talked to previously about that, and talking about electrochemical series and how we can then predict the disproportionation reactions. So what is an electrochemical cell, first of all? Well, it is a device that produces an electric current using chemical reactions, and it is formed from two half cells. So you can see this looks very similar to the standard hydrogen electrode being connected to the metal, but the biggest difference here is we actually want the electrons to be able to flow, because we're not measuring the difference between the two. We are measuring, do we get a chemical reaction happening here? So when we look at these two systems, or these two half cells, you can see that we've got a left-hand side and we have a right-hand side. And based on that information, we can look at potentially what is happening here. So when you go to your data book, you can find the equation and the E cell value for each of these two half cells. So we've got the zinc gaining 2 electrons to become zinc metal, and that E value is minus 0.76 volts. And the other one is the copper becoming copper metal, and that has a value of plus 0.34 volts. Now what we need to determine is what is happening at each of the different electrodes, because of course we can't have both of them undergoing reduction reactions, which is what this says here. And the way that we can determine this is we look at which one is more negative. The more negative value is going to be the one that is being oxidized. So the more negative value pushes the position of equilibrium to the left, and that is therefore the left-hand side electrode, whereas the more positive value pushes the equilibrium to the right. So at the negative electrode, we then get this zinc losing the ions, losing electrons to become an ion, and we get the copper ions gaining electrons to become copper at the positive electrode. So the overall reaction, when we cancel out the electrons, is we have zinc metal and copper ions becoming zinc ions and copper metal. So our zinc being oxidized and our copper being reduced. It is extremely important that we can describe how the charge flows in an electrochemical cell, and we make the distinction between what flows in the wires and what flows in the salt bridge. So in the salt bridge, it is the ions that can flow. Remember, electrons cannot flow through liquid. They can only flow through an external circuit like the wires, which is what connects the two electrodes. So your electrons are through the external circuit, whereas the ions flow through the salt bridge. But because they're all charged particles, we still get that movement of charge, so we get a current forming here. And the electrons will always flow from the metal with the more negative value to the more positive one, meaning they will flow from left to right, because the left is the one that is being oxidized and the right-hand side electrode is the one that is being reduced. And we use the values to tell us this, and it links into this position of equilibrium. Now, when we're drawing out these electrochemical cells, as you can imagine, it's not easy to consistently draw that full diagram. So what we can do is we can use a shorthand notation, and that shorthand notation is built off of the equations that we've been previously looking at. So an example for a half cell, if we take the zinc half cell, would have the zinc ion with its state symbol, and then we have a straight line to indicate a phase boundary, i.e. a change in state. Then we have the zinc solid, and we of course always quote it with an E naught value of minus 0.76 volts, and you can look that up in the data book. So some other examples would be the magnesium to magnesium solid with an E value of minus 2.37 volts, and so on. So that vertical line is there to indicate the phase boundary, so you can see that we don't have the electrons here, and we take away the reversible arrow sign as well. If we use an electrode between the solution and an external circuit, for example, if we have two ions in the solution that are undergoing the reaction, then we have to include this in the notation. So for example, if we have an iron where we use a platinum electrode, we have the platinum with a phase boundary, and then we have the Fe3 plus aqueous and the Fe2 plus aqueous, and you can see that we use a comma here because there is no phase boundary between the two ions, so we don't use that vertical line. We only use that when we have a difference in the state symbol. If we were drawing out the hydrogen would be the H plus aqueous, which would then have the phase boundary to the half H2 gas, and a phase boundary for the platinum electrode. So it's important that you get into the habit of writing out these shorthand notations for the electrochemical cells. We can then combine these two half equations into a full electrochemical cell, and we can again represent it with the shorthand notation. And we follow two main rules with a third important point. So when we write these out, the reduced forms of the species are always on the outside. So at either end of the notation should be your reduced form. Your more positive electrode, which is the more positive E0 value, is on the right-hand side, and we denote the salt bridge by using these two vertical lines that are both dashed. So for example, if we think back to our zinc and copper cell that we were looking at, we would have the zinc solid, because that's the reduced form, with the phase boundary to the zinc 2 plus. I then have my salt bridge, my two dashed vertical lines. I have my copper ion, my phase boundary, and my copper solid on the outside, because again, that is the reduced species. And this is showing the two different cells, the two different half cells that make up this cell. So the copper being the more positive value, which is on the right-hand side, and the zinc being the more negative value, which is on the left-hand side. We can also show the standard electrode potentials and the EMF of this cell all together. So this is just rewriting the same thing that I just previously wrote. The only difference is I now have the E0 values underneath. And then, of course, if you remember, this being the left, that being the right, to get the E0 cell, you always do the right-hand side minus the left-hand side, which would be 0.34 minus 0.76, which is, of course, 1.10 volts. So we would quote that along with the entire cell diagram. So we've got the shorthand notation with the E cell value. These values at the bottom are not always necessary. The most important one is the E0 cell, but you can quote these underneath so that it can help you work out what the EMF of the cell actually is. So reminder, to calculate the EMF of the cell, we always look at the E0 values. So to do that, we do the right-hand side electrode, which is the more positive value, minus the left-hand side electrode, which is typically the more negative value, and we do not change the signs, even though technically this is a reduction reaction on the left-hand side, an oxidation reaction on the left-hand side. We keep the sign exactly the same. So we don't make any changes to the E0 values when we flip the equation. And the standard electrode potential of a substance remains the same no matter whether you read the half cell forward or whether you read it back. And we always calculate it using this method. So the E0 right minus the E0 left. Now what's important to realise is that in this case, we're saying the more positive is on the right-hand side. This would be for substances that we know are feasible. When it comes to feasibility, and i.e. will this reaction happen, we can't make an assumption about what's the right and what's the left just from the values, and we'll look at some examples of that in just a few minutes. The other one that is slightly different is when we're measuring the standard electrode potentials. When that happens, the standard hydrogen electrode is always written on the left, every single time. So regardless of whether you have a positive or a negative value, the hydrogen is always on the left and the metal is always on the right. So with the copper, that gives us the positive value. With the zinc, that gives us the negative value, but it doesn't matter. We still write it so that the standard hydrogen electrode is on the left and the metal is on the right. Now we can use these values to help us determine thermodynamic feasibility. So for example, we want to know, will zinc displace copper from an aqueous solution containing copper-2 ions? In other words, if I have zinc plus copper-2, will I get the zinc 2 plus the copper? Now we know that this is going to work. Okay, we already know that this is a feasible reaction because we previously looked at it as an electrochemical cell, and you can work this out using the reactivity series. But the reactivity series comes from these values. So what we're doing is we're explaining why this happens, and we're linking it to thermodynamics and feasibility. So in order to do this, we look at the E0 values. So we pick out our two equations from the data book. And we write the two equations one under the other. And when we look at it, what we do is we start by circling the species that we start with in our reaction. So we said that our reaction was going to be the zinc plus the copper-2 going to zinc 2 plus the copper. So we circle the zinc metal and we circle the copper-2. Now we look at the values of the E0 to tell us the position of equilibrium and what way it prefers to move to. So the more negative value, remember, always moves to the left. So we are moving towards our zinc 2 product. And for the copper, because it's more positive, it always moves to the right, moving towards our copper product. So this particular reaction, because the equilibriums move in the way that we want them to go from the reactants to the products, this is thermodynamically feasible. In other words, this is the right-hand side electrode, this is the left-hand side electrode. Now notice I didn't jump to that conclusion by using the values. The values are supporting this, yes, but I need to figure out what one is the left and what one is the right by looking at what we start with. And I can then determine that my E cell would be 1.10 volts, which would be a feasible reaction. I can do a similar thing looking at zinc and dilute sulfuric acid. So this is the equation where we start with the zinc metal and the hydrogen ions, because remember the sulfate is going to be a spectator ion, and we want to move to get to our products of zinc 2 plus and H2 gas. So I'm going to circle my reactants, and then I'm going to circle my reactants in my equations. So remember, you lift the equations straight from the data book. That is where you will find these equations plus these values. And I want to make my products here. So I'm going to look at the values and I'm going to figure out what way my equilibrium shifts. So with the zinc, it is more negative than the hydrogen. So this is going to shift to the left-hand side, making this the left-hand side electrode. And the hydrogen, with it being 0, is going to be moving to the right-hand side, making this the right-hand side electrode. And again, we can work out our E cell is going to be 0 minus 0.76, which gives plus 0.76 volts. So this is a thermodynamically feasible reaction. This is why zinc will react with dilute sulfuric acid. This is backing up what we already know from the reactivity series. When I look at copper, I see something different. So you can notice with this reaction, all I've done is swapped out the copper equation for the zinc one. So I've got rid of the zinc and I've put in the copper. And again, I'm going to circle what I start with. And I'm going to do that in the equations here. And I want to be moving towards the copper 2 and the hydrogen. So I look at the values and I can see right away that this E0 value for copper is positive. The more positive one, the equilibrium moves to the right, and the more negative, the equilibrium moves to the left. So you can see that we are now not moving towards our products. And because these are moving away from the products, the equilibrium is not backing up our reaction here. And because the equilibriums are not backing up our reaction, this tells us that this particular reaction is not thermodynamically feasible. And we actually already know this from our knowledge of the reactivity series, because we know that copper does not react with acid, and we're backing it up here. If we have the reverse reaction, which is going from the copper ions to the hydrogen, so reacting with the hydrogen, if we have our Cu2 plus and we write out our numbers again, which was plus 0.34, and then we have our hydrogen, and that is, of course, 0. When we look at this particular reaction and we start with the Cu2 plus and the H2, the more positive value, remember, is shifting the position of equilibrium to the right. That's shifting the position of equilibrium to the left, giving us the reactants and products that we want. So this reverse reaction is thermodynamically feasible based on the information that we're given with these standard electrode potentials and with the equilibriums, because this time our equilibrium is backing it up. This particular reaction, though, however, does not actually take place. It will not take place under these standard conditions, and this is because there are kinetics to take into account here. And this reaction has a particularly high activation energy, so the reactants are kinetically stable. If we want to react copper ions with hydrogen, we would need to provide a large amount of heat, and that would then move it away from our standard conditions. There is an alternative method of using the E0 values to determine thermodynamic feasibility, and this involves reversing one of the half equations and changing the sign. So we've already seen that we reverse one of the half equations because we know that one of them must undergo oxidation, but we haven't touched any of the signs. Technically, you can do this and you will get a correct answer, but it is an imperfect science. So we try and advise you to avoid this, and you simply stick with your E0 of the right minus the E0 of the left, and you figure out which is the right and which is the left, not using the values, but by looking at what you're reacting and do you then make your products. So remember, you cannot, for a feasibility question, rely on the reactants, just on the values, you have to look at the reactants and products. If we take that first reaction that we looked at, what we would do is, rather than having our negative 0.76 for the zinc like we did here, we reverse this reaction and this becomes positive, and then now we add the two together. So in the way that we would normally do, we would subtract the right minus the left. This time we change the sign of one and we add them together. As I said, we do get the same answer, but it is an imperfect science, so I would avoid doing this in an exam. Looking at another reaction where we've got the manganese oxide and reacting with hydrochloric acid, under standard conditions with the standard electrode potentials, this tells us that this reaction is not feasible. However, if we were to change away from standard conditions and increase the concentration of the hydrochloric acid from 1 up to 10 moles per decimeter cubed, then what's going to happen is we're going to increase the concentration of the hydrogen ions, and we're going to increase the concentration of the chloride ions, and this then shifts the equilibrium in the direction that we want. This would cause the electrode potential for the manganese to become more positive and the electrode potential for the chloride to become less positive, but the problem here is we're changing the values. So this reaction could potentially happen and become thermodynamically stable or thermodynamically feasible. However, it is under non-standard conditions. So we do need to think about some of the limitations that we have in terms of predicting thermodynamic feasibility using these standard electrode potentials. We're always talking about it at 100 kilopascals of gas, 298 Kelvin, and 1 mole per decimeter cubed. But if we change some of those, we can make an unfeasible reaction more feasible. So the key information about thermodynamic feasibility is we can predict it using the standard electrode potentials. Even if they do predict feasibility, sometimes the reaction may not take place, and that can be due to the fact that they're kinetically stable, or it's not occurring under standard conditions. We can alter these standard conditions to make an unfeasible reaction feasible, but this can alter the electrode potential and change the position of equilibrium in a half cell. You are not expected to be able to say what happens to the value once this equilibrium changes. That is not covered in the A-level course. You just need to know that changing the conditions can make it feasible. Now, we can also use standard electrode potentials to tell us something about disproportionation. And if you remember back to topic 8 when you did redox in year 12, disproportionation is when one element or when one species is both oxidized and reduced in the same reaction at the same time. A typical example being copper 1 being converted into copper 2 and copper atoms. And again, we can go to our data book and we can pull out the key equations that we need for this to happen. And we can then use these to tell us something about the disproportionation and determine, is it feasible? So we start with copper plus and each one, and we go to copper 2 plus and copper metal. So again, we write out our two equations, one on top of the other, and we identify what we start with. So we circle our Cu plus and our Cu plus. And we look at the values. So our 0.15 is less than 0.52. So this is the more negative value, meaning our position of equilibrium shifts to the left. Whereas the more positive value, our position of equilibrium shifts to the right. And you can see this then makes the two substances that we want to make. Therefore, this one is thermodynamically feasible. So copper can disproportionate into copper 2 plus and copper metal. And you've seen this reaction before. We're just backing it up here with the thermodynamic data. An alternative one is to look at iron, and this comes up in exams sometimes. There's been past paper questions about looking at copper and iron in the same question, and we want to know, will this one disproportionate? So will we go from iron 2 to iron 3 and iron metal? So we do the same thing, we circle what we start with, and then we can't make the assumption of what one is the right-hand side and what one is the left just from the values. Remember, you must always look at what you start with and what you want to make. We would want to be making the FeS and the Fe3+. So now we look at what the values tell us. The more negative one is going to shift to the left. The more positive one is going to shift to the right. That makes this one the right-hand side, and that would make this one the left-hand side. The problem here is that these equilibriums do not match up with that. That is not what we want to be happening. In reality, what we actually want to be happening is we want this one to be the right and this one to be the left, because we want our equilibrium to be shifting from the Fe2 plus to the Fe metal and from the Fe2 plus to the Fe3. So if we take what we want, which is this one, and we do right minus left, we get minus 0.44 minus 0.77, and you can see right away that is going to give you a negative number. And as soon as you get a negative value for E cell, this is not thermodynamically feasible. So again, our equilibriums are not being backed up by the values that we want them to. Their equilibrium is not backing up the movement that we want. And when we get that negative number, it tells us that iron does not undergo disproportionation reactions, whereas copper does. The last part of this topic is then making the connection between these E cell values and the total entropy change, so linking the EMF and the entropy. And we can write this out in an equation to show the relationship. So the equation is T delta S total, so temperature times your total entropy, is equal to N, a number of moles, times F, which is the Faraday constant, times E naught cell. Now, N is the number of moles of electrons that are involved in the reaction. F is the Faraday constant, which you don't actually need to know anything about. The most important thing is that both of these values are constant. So if they are constant, we can remove them from the equation. We also carry this out at a constant temperature, which is always 298 Kelvin. So we can then get rid of the T, the N, and the F, because these are all constant, and that leaves us with the total entropy and the E naught cell and the EMF. And what this tells us is that the total entropy change of the cell is proportional to the EMF of the cell, meaning if the total entropy is positive, your EMF should be positive as well. So if your E cell value is positive, that must mean that the reaction is thermodynamically feasible, because your total entropy is also positive. And we know that that means thermodynamic feasibility, which we covered back in topic 12. If we show you an example, we can see the zinc and the copper. When we write out the two half cell reactions and we get this overall reaction, and we see that we get this positive E cell value, that tells us that this positive value means it is a feasible reaction, because that would give you a positive total entropy. And when you have a positive total entropy, it means feasibility. Whereas for the second one, if we look at the hydrogen, and if we were to have this as an electrochemical cell, because we get a negative value, this would not be feasible, because our E cell is negative, which would mean our total entropy is also negative, which means it is not feasible. So we can make the link between the EMF of the cell and entropy, with the two things being directly proportional to each other. We can also then make a link between the equilibrium constant and the EMF of the cell, because we already know that there's a link between total entropy and equilibrium constant. Again, we learned this back in topic 12. So if we were to take the previous equation that we just looked at, which is this one here, and I've just rearranged it to make the total entropy the subject, and I then substitute in that total entropy for the R natural log of K, again, I look at what all the constants are, and R is the gas constant, N is the constant number of electrons, Faraday constant is, of course, also constant, and the temperature is always constant. So again, at a given temperature, the natural log of the equilibrium constant is proportional to the EMF of the cell. So we can use the EMF of the cell to calculate the equilibrium constant. So we are now linking together topics 12, topic 13, and now topic 16. Now, they don't necessarily want you to use this equation in an exam. What they want you to be able to state is that you understand that there is a link between the EMF of the cell, the equilibrium constant, and the total entropy, and these things are all directly proportional to each other. That's the takeaway that they want you to have. As always, let's finish off with some past paper questions. So this is a question from the June 2018 paper, and this is just a very straightforward one, so you might want to have a look at some more challenging ones as well. We've got potassium dichromate in acidic conditions as an oxidizing agent that we use in organic chemistry. We already know this. We've seen this back in topic 15. We are going to prove why it works by using some of the electrode potentials. So we, first of all, are given some information in the table. Notice that we're given 3 equations. So at some point in this question, we are going to use all 3. And we want to deduce the ionic equation for the oxidation of ethanol to ethanal by the potassium dichromate. So in this case, we are going to be looking at ethanol, which is present in this one, to ethanol and the potassium dichromate. So we're looking at plus 133 and minus 0.61. Now, because we're not looking at feasibility here, we already know that this one is going to be the right-hand side electrode. This one is going to be the left, because the more negative value is the left. That means that this position of equilibrium will shift that way, whereas this position of equilibrium would shift that way. So in other words, we are going to reverse the top equation. And when we reverse the top equation, we of course also need to get rid of the electrons. So we would need to multiply this top one by 3 as well to make it up to 6 electrons. And we can cancel out any like terms, so our hydrogens are going to cancel out. And when we do all of that, we will eventually get an answer of the dichromate plus 8 hydrogens, because we will have 6 being cancelled out on the other side from the middle equation, plus 3 ethanols. And that is going to give you 2 chromium 3 pluses, so I'm just lifting this straight from the equation, plus 7 waters, plus 3 ethanols. So we're going to have to reverse and do some multiplication and make sure we balance out all of the like terms. Okay, and you can have an arrow or you can have it as your equilibrium. Either one would be acceptable. They're not going to take a mark off for that. You get 1 mark for making sure you have all the correct species and no electrons, and the second mark for making sure it's all fully balanced. We're going to stick with these same substances, but this time we want to look at the E cell for each of them. So we want to calculate the E cell for the oxidation of biacidified potassium dichromate of the ethanol to the ethanal and the ethanal to the ethanoic acid. So looking at these values, we can see that both times these two are going to be the left-hand side electrode because they're the more negative, and this one will always be the right. So if we take the first one, we calculate E cell by doing the right minus the left. And so right is 1.33 and we minus, and the first one is ethanol to ethanal, which is this one. So we do minus 0.61, which in other words, we add them together and we get plus 1.94 volts. For the second one, we use this top equation and we do exactly the same thing. So we take the right-hand side electrode and we subtract the value for the left-hand side. So we get 1.33 minus 0.94. And in other words, we add them together and we get a value of 2.27 volts. Both of them being positive values, we know then that both of them are feasible because of that positive EMF of the cell, and that makes sense because we know that this reaction happens. We've seen it back in topic 15. So again, we're backing up something that we already know. And the last part is looking at potassium manganate being another laboratory oxidizing agent, which is used in organic chemistry. And we want to use the data booklet to answer the question. And we want to suggest why potassium manganate is not used to oxidize alcohol such as ethanol, whereas potassium dichromate is. And we want to give the relevant electrode, standard electrode potential plus the reaction. We don't need to do a calculation, we just want to comment on it. So you would be able to go to your data book and find the manganate, and the equation is MnO4 minus, and you lift this just straight from the data book. Don't need to change anything, plus 8 hydrogens plus 5 electrons, and that would go to manganese 2 plus 4 waters, and the E value that goes along with that is plus 1.51 volts. That's the first mark, purely just lifting it straight from the data book. And now we want to look at why that one is used why this one is not used in comparison to the other one. And what we see is that this has a more positive E0 value. Because it's more positive, that tells us that it is a stronger oxidizing agent. Now, this is a problem because if it's a stronger oxidizing agent, we may not have the oxidation stopping at where we want. If we use the potassium manganate, we may not make the ethanal. If it is a very strong oxidizing agent, it means that we could potentially go straight to the ethanoic acids and not be able to do that first step. Whereas when we use the potassium dichromate, our oxidation is a little bit less because it's a weaker oxidizing agent, so we can do it in steps. There's the mark scheme for those 3 questions, and you can have a look at how the marks break down and potentially what are some alternative answers. That's everything for topic 16A. I would strongly recommend that you find some past paper questions and you try these and put into practice identifying what is the right-hand side and the left-hand side electrode using the values, but also using the reactants and products from your equation that you want to happen, and then linking that to feasibility. If you have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.